Explain how ions are accelerated, detected, and have their abundance determined in a time-of-flight mass spectrometer. So how are they accelerated? Well, the ions pass into the mass spectrometer where they are ionised, and they're ionised so that they can be accelerated and detected. So making them positive ions is something to do with it. They actually then pass in and they're accelerated by an electric field. So there's a negatively charged plate in that electric field that will attract the positive ions. So we need to say that they are accelerated by an electric field. And then how do they have their abundances determined and how are they detected? Well, they're detected when they hit the detector at the end and gain an electrons. Sorry about that. Pen's playing up. And their abundance is determined by the size of the current generated when they gain electrons. So when they gain an electron, they generate a current. The bigger the current, the more ions must have hit the detector at that same time. So abundance is determined by the size of the current generated at the detector. Calculate the mass of a single chromium 52 plus ion. So remember that this 52 is the mass of 1 mole in grams. The molar mass is in grams per mole. So 52 grams per mole. So this is the mass of 1 mole of chromium ions in grams. Now we want this mass in kilograms. So the first thing that we're going to do is do 52 times 10 to the minus 3 to make that be in kilograms. And then we're going to divide by how many are in 1 mole to find out the mass of each one. Now remember that ions are very, very small, so we should be looking for a very, very small number. And if you're getting a big number, you've done something wrong with Avogadro's number. So 8.64, or if we give it to 4 significant figures, 8.635 times 10 to the minus 26 kilograms. So there's a minus in there. 8.635 or 8.64 times 10 to the minus 26 kilograms. In a time-of-flight mass spectrometer, the kinetic energy was 1.269 times 10 to the minus 13 joules. Calculate the velocity. And they've given us the equation, so we need to do a bit of rearranging. So I'm just going to times both sides by 2 to get rid of the half. So we'd get 2 times kinetic energy is mv squared. If we divide both sides by m, we'll get v squared is 2 times kinetic energy divided by m. So to find velocity, we're going to do the square root of 2 times the kinetic energy divided by the mass. So we're going to, in our calculator, use the square root of 2 times the kinetic energy. So I'm going to put that in a bracket on the top line there, keep the square root sign going, over the mass that I've just calculated, 8.635 times 10 to the minus 26. So on your calculator, you can press the square root button and then use the fraction button to make your calculator show you the calculation in exactly the same way that you've written it, so you can check it. When I've typed that on my calculator, I'm getting quite a large number. It's on my calculator screen, it's reading 1714409.79. That's far too many significant figures for the answer. I'm going to give my answer to 3 significant figures because I haven't been asked, and that's quite common in chemistry to be 3 significant figures. I'm going to move the decimal place and do it in standard form. So I'm going to go 1, 2, 3, 4, 5, 6. So 1.71 times 10 to the 6 meters per second. Then we've been asked bromine has two isotopes, 79 and 81, and they're in equal abundance. So if our abundance is in percentages and these are in equal abundance, then there would be 50% of each one. Bromine forms ions with the formula Br2 with a positive charge. Sketch a pattern of the peaks you would expect in the mass spectrum of a sample of bromine. So we need to think about what we would be expecting. We've got Br2, so our first Br could be a 79 Br or an 81 Br, and there's a 50-50 chance of that. And our second bromine in our Br2 could be a 79 or an 81. And we've got a 50-50 chance of that, so a half chance of each. So if I were to follow that first path, 79, 79, it's going to add up to, if you add up two 79s on your calculator, 158, and a quarter of the sample will end up there, because it's a half times a half. If we follow each path, a quarter ends up in each direction, but 79 add 81 is 160. 81 add 79 is also 160, so a half of the sample ends up weighing 160, and then a quarter ends up weighing 81 add 81, 162. So we're looking for three peaks, one at 158, representing a quarter of the sample, so up to this 25% line. Try to line it up a bit better than I did there, with 158. And then half the sample at 160, so up to the 50% line, and a quarter of the sample at 162. So three lines in a 25 to 50 to 25% ratio at 158, 160 and 162. A sample of xenon with an AR of 131.31 consists of four isotopes. The abundance of three isotopes are shown in table 3. The data for one of the isotopes is missing, so we don't know the mass, M, or the abundance. Well, the first thing we can do is calculate the abundance, because what we know is that the total of the abundance must add up to 100. So let's first of all calculate the abundance. So 100 minus 28 minus 25 minus 27 is going to leave us with what we've got for the final isotope. So if you type that into your calculator, you'll find that you've got 20% left. So this is 20%. Then we want to use the AR calculation. Now the AR calculation says that the relative atomic mass is equal to the sum of the mass times the abundance. So the sum of 129 times its abundance 28 plus 131 times its abundance 25 plus 132 times its abundance 27 plus 20 times M, we don't know what M is, that's what we're going to try and find out, divided by the total abundance, which in this case would be 100%. So I'm going to times both sides by the 100, so I get 13131. I'm going to expand out these brackets and add up the three that I can add up. So I'm going to do 129.28 on my calculator, plus 131.25s, plus 132.27s. That's coming to 10,451 plus the 20M. So now I'm going to subtract 10,451 from 13131. So I'm getting 2680 equals 20M. Then I'm going to divide both sides by 20 to find out the mass number of the final isotope, and it's coming to be 134. So we were asked to show our work, and so we can't just do this question by guessing. We do need to show the answer. It must come out to be a whole number because it's the mass number of an isotope.